Hello everyone. We have been looking at adsorption, right? We are changing the phase of one or a set of compounds, not one compound. In water, you are going to look at removal of multiple compounds of interest by adsorption. And you want to change phase, as in one phase is water, we don't want it to be in the aqueous phase, and you want to remove it and adsorb it onto another surface, let's see, right? Which is the activated carbon, the example that we are looking at, or the media of interest that we are considering, right? Here I want to be able to understand how much to use, and if I use a certain amount of certain characteristics and certain surface area, what will be the final concentration of my effluent if the influent concentration is this, and so on and so forth. So here we obviously have to look at the surface area, the concentration of the relevant solids in that particular volume, yes, how much volume of water is going to come in contact, and more importantly the concentration initially and after equilibrium has been reached or it's going through the relevant system. So let's look at these aspects. So we are going to look at adsorption isotherms, which to understand the relationship between Q, the concentration of the relevant adsorbate on the adsorbent, and how it relates to the concentration of the adsorbate in the water, right? So let's look at this. So isotherms are used to select the manufactured activated carbon and so on and so forth. Isotherms relate Q to C, and this is something I already mentioned. So what do we have? How do I get this particular Q and such? So add the same initial target chemical concentration in each of them, right? And different activated carbon dosages in each. So the compound of interest C initial, the concentration of the compound of interest initially is the same, but the dosage is different. You see, relatively less, more media, and then one control. So after, let's say, 6 days, or depending upon the kind of compound, 4 days or such, you are going to mix it and then let it reach equilibrium, and then you are going to check this. What is this Q? Q final, it's milligram per gram units. Let's see how it comes. In the numerator, you are going to have C initial, let's say, concentration of the adsorbate initially and after equilibrium has been reached, right? So that's the relevant, what do we say, concentration by concentration of the relevant solid, grams per liter, right? So milligrams per liter by grams per liter, let's see. So then you are going to end up having milligrams of the compound adsorbed per gram of the relevant solid, right? And then adsorption isotherm is a Q versus C relationship. More importantly, this is always at equilibrium. Keep in mind, at equilibrium. Equilibrium is a state when the system has gone to the furthest extent possible, or has been allowed to reach the furthest extent possible at the given temperature and pressure. So it gives you an idea about how far the system can travel, layman's terms, right? So isotherm preparation, we will look at one particular or set of data later, prepared from experimental data obviously. Selected activated carbon is placed in a solution, as we just talked about, containing the chemical of interest, right? The solution is well mixed to provide contact between the granules of carbon and the relevant adsorbate or the chemical. So it depends, the time depends, 4 hours or 6 days, it depends upon the type of compounds. Initial concentration will decrease. Why will this concentration decrease? So initially, if this is my media, well, the media is never going to have such flat surfaces. I am just using that because I am a poor, poor at drawing. So this is the compound. So after some time, what will happen after equilibrium, let's say 6 days or 4 hours or such, this is my media, and some of the relevant compound will be adsorbed, 1, 2, 3. So 2 moles in the water while 3 moles are adsorbed. This is after 6 days. So equilibrium has been reached. That is what we are assuming, let's see, right? The initial concentration is decreasing, right? Now earlier there were 5 moles per, let's say this is 1 liter of water. Here now there are only 2 moles per 1 liter of water, because 3 moles are adsorbed onto the relevant solid. So that's something to keep in mind. Initial concentration will decrease to an equilibrium value, and then you can plot it and get the relevant relationship, let's say. And right, we will look at this again. So types of isotherms, there are different relationships depending upon the types of compounds, the mode of adsorption and such. We will look at the most simplest one, which is rarely used. This is the linear isotherm, right?
Q, we are saying that it's linear to the, or Q is linearly depend upon the concentration of the compound in the water, right. It is the partitioning coefficient, Kd is the partitioning coefficient, but here it says more or less like if this is very high, even Q will be very high, but that is never going to happen. Why is that? Because your media has, at the end of the day, certain properties, certain limited surface area. So it's not as if you keep increasing the concentration, the Q also is going to increase, let's say, right. If this is C and Q, fine, this is reasonable, but it's never going to be like this, right. If not that slope, it's not going to be ending up looking like this, let's say, right, because there you have thresholds. So this is rarely used, yes. And here we are going to now move on to looking at Langmuir adsorption isotherm. Here we are going to assume that there are limited number of sites, right, and there is an equilibrium between the compound, the sites available for adsorption, and the adsorbed sites. So that's what we are going to look at. So equilibrium between surface and solution, and we are assuming that it's a reversible chemical equilibrium between these species. The species are the surface and the relevant compound, let's say, right. The adsorbent surface is made up of fixed individual sites. So we have a limited number of individual sites, let's say, where the adsorbate can be chemically bound, let's say, or can be bound if not chemically bound, right. So here we have, this is the site, this is the relevant, okay, this is I think the compound and this is the area. Let's look at the relevant nomenclature, and this is the relevant bound site, let's say, compound being adsorbed onto your relevant site. Let's look at the nomenclature. Okay, this is the vacant site, SV is the vacant site, millimoles per meter square. Adsorbate species in solution, this is the concentration in the aqueous phase, this is the vacant sites available per meter square, and this is the sites that have been adsorbed, let's say, adsorbed species bound to surface. So there is an equilibrium between this, so it can go one way or the other, that's something to keep in mind. Langmuir adsorption isotherm, so let's take this forth. So we are looking at this Langmuir adsorption, and one fundamental aspect about this is we are assuming that we are only going to have one layer or mono layer of adsorption. So this is my site, and once all these sites have been taken up, that's it, you are not going to have other layers, let's see. So that's one aspect, because as you saw, or as we discussed with respect to physical adsorption, where van der Waals forces of attraction are relevant, especially in the context of granular activated carbon, you can have different layers. It's not only going to be mono layer, right? It's relevant over larger or longer distances. So that's one aspect to keep in mind. We'll come back to that. So equilibrium condition can be written as, so we have that SV vacant sites plus the relevant compounds being in equilibrium with the adsorbed sites, let's see, right? So if this is the equilibrium constant K, right, that's going to be equal to products by the reactants, right. So that's what we have, products, which is the SVA or SEA by SV, number of vacant adsorbed sites into the concentration of A, right. And that again, delta G, this is pretty, this is something that you know of, equilibrium relationship K and delta G naught, let's say, right. Again, we are concerned mostly with this, but now you can see the effect of temperature. As you increase or decrease the temperature, you can see how K will be affected, and thus this equilibrium between SVA and SVA, right, that's something to keep in mind. So what do we have here? KAD is the Langmuir adsorption equilibrium constant, yes. Ca, obviously, as I mentioned, is the concentration of A in the relevant solution. Delta G naught is the free energy change for adsorption. R and T, that's something that you know. Fine, this is something that I have. Let me see how I can use this to get it done. But I want to be able to get a relationship where I end up with Q and C, right? How do I do that? For that, I will use the relevant assumption that S total, there are fixed number of total sites, let's say, right? Some are vacant, some are adsorbed, right? SV plus SA, right? So some are adsorbed, and SV, we know that we can get it from this relationship here, right? SV, let's see, right? SV, we can get that relationship here, and now we can write it in this terms, let's see, right? St is equal to the total number of sites available or monolayer coverage, let's see. Rearranging, we are going to get this particular term, right? But this is in millimoles or moles per meter square, let's say. But here my units are milligram of the adsorbate per gram of the adsorbent. Let's see how we will go from here to there. One is here its area, millimole of adsorbate or my compound per area of adsorbent, right? But I want to have milligrams of adsorbate per gram of adsorbent. So how do I do that? One is molecular weight of the adsorbate and the other one is area per mass of the adsorbent. So I have to multiply it with that. So let's see. So how do I get Q? This is what I had earlier, moles per meter square, by multiplying with AD, which is meter square per gram, and molecular weight, which is grams per moles. I will end up with milligrams per gram, let's say milligram of adsorbate per gram of adsorbent. That's what we discussed earlier. So then this is going to end up like this, and Q max, right? Q is equal to Q max, right? So it depends upon S total. Let's see where I guess I have that, right? You have S total and I multiply it with my particular area and molecular weight and such. I will end up getting Q max, right? So that is what I have. So I end up with Q max, and the relevant terms BA is nothing but this K, and C is the concentration of the compound at equilibrium. So what do I have? I have Q is equal to Q max. There is a certain limit. It's a maximum. It's limited by a particular threshold. B into concentration of the compound in the water at equilibrium plus 1 by B C, let's see, right? B is also K. Again, please note that the key aspects are we are having a relationship between Q and C, and here we have a equilibrium constant, or which we are calling as Langmuir adsorption constant of adsorbate, right? So this is a function of two aspects, both the adsorbate and the adsorbent. So that's something to keep in mind, and it's also going to have a Q maximum. So that's what we have here, right? And these are the general aspects which we already discussed. As I mentioned, Q maximum, S total, area of adsorption or surface area per gram of adsorbent, right? Surface area available per gram of adsorbent into molecular weight of your adsorbate, right? So that's something we looked at. Linear form of Langmuir adsorption isotherm. Sometimes I want to see the linear form so that I can fit the data relatively easily. So if I play around with the variables, this is what I end up with. As you can see, if this is y is equal to mx plus c. So this is my intercept, m or x, y is this, x is my other, this one, ca is my x. So m, the slope is 1 by qm, right? And my intercept is 1 by ba qm, right? That's something to keep in mind, right? So let's look at the shape of this Langmuir isotherm. Q is equal to Q max into BC by 1 plus BC. So again, note that different people are using different nomenclature, but one aspect is you are always going to have a maximum and the relevant coefficient here, let's say adsorption constant. So this is the Q max. As you can see, there is going to be a maximum, right? So that's something to keep in mind. On the y axis, you have Q. On the x axis, you have the dissolved adsorbate concentration at equilibrium, let's see, right? So at 1 by K, if you think of it, this is like our monokinetics, right? Where you have mu is equal to mu max into S by, I think, Ks plus S, and so on and so forth. So you can look at the relationship and so on and so forth. But here again, similarly, we have the relevant setup. At 1 by K, Q equal to, I guess, 0.5 Q max, at Kc is equal to 1. K into C is equal to 1, I guess, right? Okay, if K into C equal to 1, yes, you see that Q max, Q is equal to Q max by 2. So that's something to keep in mind, right? And slope when Kc is far less than 1 is Q max K, right? When Kc is far less than 1, I guess is Q max into K. Okay, that you can see from the relevant relationship. So this is how the Langmuir isotherm is going to look like, right? It's going to approach a maximum at the later. So here, even though you are increasing the, what do we say, concentration, right? What do you see here? Let's say, let's compare this at a particular C value. This is the relevant case. At a particular C is a particular Q. And even here, right, you can see the relevant efficiency of removal both at higher and lower concentrations, right? That's something to keep in mind. So Freundlich isotherm, let's see. So we were looking at Langmuir until now, right? Langmuir, where we have a threshold, and another aspect is it's mono layer, right?
But we know that especially with granular activated carbon, where you have hydrophobic compounds being adsorbed onto the media, and the key aspect is that we have van der Waals forces of attraction, which do not limit the adsorption to only one layer but multiple layers, right? And thus we see that rather than Langmuir, for the relevant granular activated relevant adsorption, Freundlich isotherm is relatively more, what do we say, or a better fit. It's an empirical equation that is used to describe the results of adsorption isotherm, especially for granular activated carbon. So Q is equal to K, right, the capacity, and Ce 1 by n. Here 1 by n, sometimes people use n, so you have to look at it before you look at the relevant units or applications, let's say. This will give you an idea about the intensity, K will give you an idea about the capacity, let's say, right. QE is equal to obviously mass of the solute adsorbed, let's say, adsorbate per adsorbent, right, and K is the Freundlich adsorption capacity parameter, and Ce is the equilibrium concentration of solute, and 1 by n is Freundlich adsorption intensity parameter, as I mentioned, which is dimensionless. But again, some people use n, so you have to look at that. Again, this is a pretty good fit, or typically explains the adsorption onto activated carbon pretty well. That's something to keep in mind. And thus n will depend upon temperature, as you can see here, right, enthalpy and such. We will not go into that in detail here, right. One aspect is n will depend upon temperature. That's something to keep in mind. So Freundlich isotherm, linear form, obviously I have Q is equal to K C to the power of 1 by n. So obviously if I take the logarithm, right, Y is equal to mx plus C, right. So here we have a comparison of the different kinds of isotherms. We have looked at adsorption isotherms, linear, rarely used, but you see the relationship between Q, the concentration adsorbed onto the adsorbent, and C, the concentration of the compound in the aqueous phase, let's say, right, but it can be different phases too. So linear, right, it's increasing linearly, and then Q with a Q max, where is that, Langmuir, I guess, right. So you see it quickly reaches a Q max saturation, and Q, with respect to Freundlich, you see the different profile out here, right. The key aspect is Q max and monolayer here. Here it allows for heterogeneous adsorption and thus different layers. So that's something to keep in mind, right. Let's move on. So we have another isotherm. We'll just look at this or look at the overview. The Langmuir, right, is going to be looking at or considering only one layer, monolayer. This BET isotherm takes it further, as in it's going to allow for different layers of adsorption. So here we are going to use the basis from Langmuir, and you are going to say there is one, and then once that is filled up, right, you are going to have another layer, and typically if the first one is assumed to be precipitation, not precipitation, adsorption, the other one is precipitation. So again, the only thing is here we are going to allow for multiple layers, let's say, right, to several molecular layers. Langmuir is for monolayer, this one is for several molecular layers. Here we are saying the first layer adsorbs and subsequent layers adsorb as if they were forming precipitating layers, let's say. That's the relevant aspect. So relevant equation, again, we are not going to mug up anything, you just need to be aware of it. But key aspect is this allows for several layers, not just monolayers, let's say, right. So you have the different concentrations, not concentration, different variables and such. You can look at those, right. So we have the more or less the same terms, Q maximum, equilibrium constant for the first layer. Yes, we had that earlier, but now we also have one for different layers, right. And here we have to keep in mind that the first layer adsorption and the other layers, we are assuming that to be precipitation. So here in this picture you can see that relatively clearly. So here, why is this plateau occurring? Here the first layer has been saturated, and after this first layer has been saturated, then you are going to have adsorption on the other layers. That's what you see out here, Q as a function of Q maximum and Ca by Ca, I guess, right. So this plateau or such that you see here is because the first layer has been saturated.
So let's move on and look at relevant, data, and look at an example. We have some experimental isotherm data. Determine the Freundlich and Langmuir isotherm parameters. First, I want to find the parameters and then apply linear regression. Linear regression, I told you how to go about it, typically looking at sum of squared errors. You can do this in Excel by setting the cells and calculating the sum of squared errors and minimizing the sum of squared errors by using a tool called solver, right? This will let you change a particular cell to either 0 or to minimum or to maximum, right? While changing this particular, how will you change this to come to 0, minimum or maximum? By changing another cell, right? So here sum of squared errors has to be minimum. So I'll say that this cell of interest has to be minimum. And what can you change? You can change my parameters of interest. My parameters of interest are k and 1 by n and so on and so forth. You can do this in Excel, right, using solver, but people use the built-in functions, but that won't typically solve your purpose in the long term. So linear regression to determine the isotherm parameters. But for ease of calculation or analysis, the question asks you to look at first linearize the relevant equation and then apply regression. So spreadsheet, obviously, meaning Excel, can be used. Let's see what is the data. We have different carbon type, the chemical, trichloroethene, I guess, temperature, pH, and so on and so forth. Equilibrium time, so considerable time has been given, so we are assuming equilibrium has been achieved. And this is the key aspect we have. TCE, liquid phase concentration, micromoles per liter. TCE, adsorbent phase concentration, micromoles per liter. Let's say this is the adsorbent phase, this is the liquid phase concentration. So you have the relevant values out here, right? So then obviously you can play around with it and change the relevant or calculate Q and C. Well, some are already given indirectly. So for the Langmuir isotherm, we are going to linearize it. There was a particular way to linearize it. So here you have Ca by Qa as the y and Ca here. Yes, in this way you can linearize it. You saw the relevant equation there. And then I am going to plot the data, right? Here my TA, I believe, used Excel and asked it to fit it directly, but I urge you to learn how to use the sum of squared errors. At this point, when we are at this point, the TA will give you a link to look at or understand how to calculate or try to find the best fit by minimizing this sum of squared errors. So here we have this y, right? This is y is equal to mx plus c. But if you look at the relevant variables, I think this particular slope was 1 by qm, right? So let's see 1 by qm. Okay, this is the linear relationship, right? This is the intercept. This is 1 by qm is the slope, right? So slope is 1 by qm. From that, I can calculate qm, let's see, right? And then I know what is the intercept, right? Intercept is this, but here note that you are having the rounded off values, so that will give you considerable error. But r square, okay, another aspect here, I guess, r square will give you an idea about how good or how well the data is explained by this model compared to the using just the average, let's see. So if r square is 1, that means it's very well explained or perfectly explained. If it is 0, it's very poorly explained, let's see, right? It is also going to take into account the sum of squared errors. So r square of 0.96 is good, but not remarkably great, let's see, right? R square of 0.96 is good, but again, I would suggest that you look at sum of squared errors, let's see, yes. But again, that might not be good to look at when you are using different kinds of equations here, right? So we'll stick with r square for now. So qm, we already have qm, and I know the intercept, which is BAQM, right? I already know QM, now I can calculate BA, right? And that's what we are going to do here. We are going to calculate BA. I am not talking in detail about the relevant units. You can play around with the units and figure out how to get that done. And then Freundlich. Freundlich was what now? Q is equal to k into c to the power of 1 by n, right? If you take the logarithm, you will linearize that. So here log q on the y-axis and log c on the x-axis. Q and Ca, you have that from your relevant equation, not equation, experimental data. And then the TA fit the relevant data here, not the data, the model. and when he fitted it, and we see that R square is now much better. Earlier it was I think 0.96, now it's 0.99, and it's y equal to mx plus c. So here with relatively simplistic analysis, we are saying that the Freundlich isotherm is doing better at explaining the data compared to the Langmuir one, let's see, right? And now let's go about calculating the relevant constants here. So let's see what we have. So this is the linearized one. Earlier it was q equal to k into c to the power of 1 by n. Now by taking the logarithm, you linearize the relevant equation. So what is the slope? Y is equal to mx. This is the slope 1 by n. From that I am going to get that, and intercept is log k. Intercept is log k, right? So that is what we have out here. From that I can calculate the relevant variables, right? So again, this is what we discussed. Freundlich isotherm provides a better fit. And then another example here. So we have Freundlich information for a particular compound. What is this compound? I guess it is for benzene, right? Adsorption of benzene onto activated carbon has been reported to obey the following Freundlich isotherm equation, where C is concentration of benzene in the aqueous phase in milligrams per liter, and Q is the concentration of benzene in milligrams adsorbed onto gram of the activated carbon. So this is what we have. So 25 degrees centigrade and all that, fine. And 0.5 milligram per benzene is to be treated. This is the initial concentration, right? Initial concentration is 0.5, right? C initial is 0.5 milligram per liter, fine. In a batch process, main aspect is batch process to reduce the concentration to less than 0.01. So final one, C final, let's say, has to be 0.01, not 0.1, 0.01 milligram per liter. The adsorbent is activated carbon with specific surface area of 650 meter square per gram. Compute the required activated carbon dose. So I guess here we just looked at general aspects. Okay, fine. So here what is it that we have? This is the final that I want, and I want to know how much activated carbon I have to put in this particular solution per liter, let's see, right? So what is the relationship? I know that this is already the relationship. So let's use that. Here this 0.01 is the one at equilibrium. This C final will be the one at equilibrium or after equilibrium has been reached. So in this relationship, obviously this C benzene is going to be equal to 0.01, let's see, right? So when I plug in 0.01 and such, looks like I will end up with Q, the equilibrium one, that's going to be, or Q, which is going to be in equilibrium with the C at equilibrium, right, is going to be 4.3 milligrams of benzene per gram of the activated carbon. So one aspect to note is that earlier, let's say this is activated carbon and this is benzene initially, 1, 2, 3, 4, 5, 6, and then later, let's say I have only one in the solution and 1, 2, 3, 4, 5 moles are adsorbed onto the activated carbon, but the total moles or total mass, let's say, is still the same, right? The total mass here is still 6, or total number of moles per volume is still 6 here, total number of moles is still 6. Why is that? Because it's a batch process, obviously, right? The total mass is conserved here. So C total benzene will be equal to the benzene in the aqueous phase and benzene adsorbed onto the relevant activated carbon. So initial one is 0.5. This is per unit volume, that is why concentration is working out. If I multiply this with volume, it will be per or with respect to mass, let's say, right? So that's something to keep in mind. So 0.5 is the initial one, and in what phases is that? One phase is still in water, right? One phase is still in water, 0.01 milligram per liter, which is the final one, and the other one is that it's present, also present in the, or present or adsorbed onto the media, and I know that it's going to be at 4.30 milligram per gram, and here I am going to have concentration of the activated carbon required. So from this equation, I see that I need to add 114 milligrams per liter of the particular solution to be able to bring down my benzene concentration from 0.5 milligrams to 0.01 milligram per liter, right? So that's something to keep in mind. Again, two aspects. We calculated Q from the particular Freundlich isotherm, and then we understood that the total moles or total mass is going to be the same when I am going to consider both the dissolved and the adsorbed phase. Initially everything is dissolved, so that's why it's C total benzene, and then afterwards some is dissolved and some is adsorbed, right. So, the dissolved one is 0.01 and this is with respect to the adsorbed one, and from that I can get the concentration of the activated carbon. Let me move on. So, another example, if the same adsorbent dose is still the same, meaning it is 114 milligram per liter is still used to treat a solution containing initially 0.5 milligram per liter of toluene, right. Again another hydrophobic compound, benzene 2 relatively hydrophobic compound. What will be the equilibrium concentration? Here they are not asking us how much activated carbon to use, but they are saying this is the amount of activated carbon that you have, or the mass per volume of the solution that you have, and if my toluene is there instead of benzene at this concentration, what is the final one going to be at equilibrium? So, the adsorption isotherm for this particular toluene is also given. As I mentioned, the isotherm will depend upon both the adsorbate and the adsorbent. So, that is why you see a different relationship here, let us say. So, mass balance again, so this is total. Before adsorption everything is only dissolved, afterwards it is some of it is dissolved and some of it is adsorbed, let us say. This is obviously per unit volume, that is why this particular concentration terms can be used here, right. Typically we look at the mass. So, 0.5 everything is present in the dissolved 0.5 milligrams of toluene per liter. I want to know what is the concentration at equilibrium, right, and I also know Q already. Q is given out here, and the C is again, you know that the concentration of toluene adsorbed onto the activated carbon is going to be dependent upon the concentration of toluene which is in equilibrium at the solution, right, not at the solution, in the solution. And you know the concentration of activated carbon, it is 114 milligram per liter. So, from that I get the concentration of toluene at equilibrium, or the final to be 3.93 into 10 power minus 4. You see that 3.93 into 10 power minus 4 milligram per liter at the same dose, initial one was 0.5. But for benzene you saw that even though initial was 0.5, the final was only 0.01. So, you see that toluene seems to be relatively more hydrophobic than benzene, and thus it wants to leave the water and will be strongly adsorbed onto your particular activated carbon. So, that is one aspect to note here. You see that the final concentration is pretty much less than the C equilibrium when you had only benzene. I think that was 0.01 milligram per liter, right. So, that is something to keep in mind. So, granular activated carbon breakthrough, what is this breakthrough? So, here this was a batch process, right, we were looking at a batch process, but in a wastewater or water treatment plant you are going to have water flowing continuously. So, you can't have batch process there, it is going to be a continuous flow system, typically a plug flow if I may say so. So, you are going to have the kind of systems that we looked at in the figure, right. You are going to have these activated carbon systems, upflow or downflow depending upon it. Let us say here, let us say I have upflow, yes, and here is my mass transferred zone. So, initially most of the compounds will be adsorbed in this zone itself, later this zone is going to go up and up. What do I mean by that? So, here I have the polluted water, here I have the treated water, and in this graph we are going to look at operating time on the x axis and C by C naught, let us say. C is the effluent concentration, C naught is the initial concentration. So, initially what is the profile going to look like? You know, nothing in the effluent, right, everything is being adsorbed. Think of toluene earlier, even though I have 0.5 initially, it was I think something like 3.9 into 10 power minus 4 milligram per liter in the effluent, that is the equilibrium concentration. So, it is more or less equal to 0, right, C by C naught is almost equal to 0. But over time what happens, most of the sites on this particular activated carbon are going to be adsorbed, right, there are no more free sites for it to be adsorbed upon. Also note that in water you are not going to have just toluene, you will have other organic carbon or organic compounds which will also adsorb onto your particular activated carbon, right. So, you will also have these competing adsorbates. So, that is something to keep in mind. So, over time you are going to have this particular activated carbon being exhausted, right, that is the term that I am using. So, here you are going to start having or seeing that the effluent concentration is going to increase, and after certain time the effluent and influent concentration is going to be almost the same. So, you will have to decide what is your acceptable concentration. Is it, let us say, something like this at this level? So, that if that is that level, then this is the breakthrough time, let us see, right. So, GAC breakthrough, let us say when you your effluent concentration is exceeding your, what do we say, objective or final concentration that you want to have. So, that is what we have. So, as time proceeds, adsorbate slowly saturates or is exhausted, saturates the GAC, and a concentration profile known as the mass transfer zone develops. We looked at the mass transfer zone, right, and moves through the bed, right. The mass transfer zone is the length of the bed needed for the adsorb to be transferred from the fluid into the adsorbent. So, this is something to keep in mind. Mass transfer zone is the length of the bed needed for the adsorbate to be transferred from the fluid into the adsorbent. And eventually, though, what is going to happen? The front of the mass transfer zone appears in the effluent, right. That is what you have. Front of the mass transfer zone appears in the effluent. That is what you see out here. And then you are going to see the concentration of your effluent increasing. And the time when the concentration exceeds the treatment objective, this is what we discussed, the effluent is called breakthrough. Let us see, we say that the GAC or the system has achieved breakthrough, let us see. And in the next session, we are going to start talking about ion exchange, right. So, there it is ion exchange, it is not just van der Waals force of attraction, but with that I will end today's session. But key aspect is we are having a media so that we can remove relatively hydrophobic compounds from the water. And what is the media that is typically used in water or wastewater treatment for this purpose of adsorption of organic compounds? It is granular activated carbon, right. So, with that I will end today's session. Thank you.